So the third application is hyperconjugation. 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 What is conjugation? That we will see in the resonating contributors. Hyperconjugation. Okay. Hyperconjugation. Hyperconjugation. So what is happening here? Hyperconjugation, where you may observe this kind of effects. See, with organic chemistry, if you observe one molecule, maybe multi effects are present. What is the dominant effect? How many effects are there? And out of all among those, which is a dominant effect? Based on the dominant effect, then you have to find. We have what? Electronic effects like inductive, mesomeric, resonance, aromaticity, hyperconjugation. Next one, field effect is there. That bond angle NBPR1 field effect is there. Next one is a spherical effect is there. SIR, SIP, and afterwards salvation effect is there. So you may observe all these factors, all these effects which are present in a given molecule. Sometimes only one is present, sometimes all are present. So out of all, which is dominant, what is happening based on the situation? Okay, this is the dominant effect. With respect to this dominant effect, maybe reactivity or stability or acidic nature or basic nature, that we have to fix at the final. Okay. Now here second, third, not second. Second is dancing resonance is over. De-resonance is over. Next one is hyperconjugation. Hyperconjugation, what is the condition here? Hyperconjugation is a free orbital. There should be free orbital. First condition is what? Whether it is having what? Free orbital as anti-bonding pi orbital. So with respect to this free orbital or anti-bonding pi orbital, there should be at least one sp3 hydrogen. So this is a condition to show hyperconjugation. There should be free orbital, or else next one is what? Anti-bonding pi orbital. Anti-bonding pi orbital, at least one sp3. With respect to this one, at least one sp3. So this is actually hyperconjugation is called the sigma pi delocalization or sigma pi resonance. Or sigma pi resonance or sigma pi delocalization. Normal delocalization, normal resonance is different. Here hyperconjugation is said to be sigma and pi resonance. What is happening here? Let's see with one example. I am taking here carbon with 2 bonds and 3 bonds here. Now this is having like empty orbital, positive charge, which means here empty orbital. So overall, how many bonds are there, beta? 3 bonds are there. This is the sp2 carbon with empty orbital. Of course, here one condition, at least one free orbital or anti-bonding orbital, which means hybridization would be sp2 beta. At least one free orbital means here sp2 is there, then the remaining p orbital is a free lobe. Whether it is free or, of course, in pi bonding also you may get hybridization. So overall, sp2 atom with respect to sp2, at least one sp3. This is the condition. Now here this carbon is having sp3. So sp3 3D representation representing this hydrogen on the plane are remaining 2 hydrogens are 3D like this. One is above plane. So if you imagine practically here, one is above plane, one is below plane. Now actually there are 3 hydrogens. Okay. So what is happening here? This is the free lobe. This will be the free lobe. Here CH bond is there. CH bond is what here? En difference is generated. In the influence of this one, En difference is, of course, again it is inductive concept. En difference is generated. So which is more electronegativity? Modified electronegativity. C is what? Modified electronegativity. So it gets what here? This bonded electrons are polarized towards carbon. So what is the charge of this carbon? That you may get like this. Here. 2 bonds are as it is. Now here carbons are 2 bonds are as it is. Now this is having what here? Empty orbital. Now this carbon, this time it is generated what here? Carbonium. So removal of proton representation is like this. And remaining 2 hydrogens are like this, below and above. Below and above. Now see here. One is what? Empty orbital. One is what here? LP orbital. So of course distance between carbon is very small, very less. So no problem here. It is getting overlap. So now what is happening here? See, Carbon carbon double bond is generated here, double bond. Next, these two hydrogens are like this. These two hydrogens. Of course, here H plus is there. Here H plus is there. See now. First one is what better? This representation is carbocation. Carbocation. This is having what here? Charge. Positive charge. The same carbon. Left side carbon. What is the carbon charge here? 0. What is the carbon charge here? 0. 0 it is. See. Carbocation 0. Carbocation 0. Next, reversible reaction also possible. This is spontaneous, what here? Equilibrium position. Next one, this is delocalized reversely, now forming the sigma bond. That's why it is called here what? First one is CH bond. CH bond is a sigma bond. Next one, it is formed what here? Pi bond. Next, delocalization backward. Pi to sigma, sigma to pi, pi to sigma, sigma to pi. That's why this delocalization is called what here? Alpha. What is that? Alpha pi or sigma pi, you may say sigma pi also. So sigma pi resonance, sigma pi resonance, sigma pi delocalization. This is because of which one? This bond is formed, pi bond is formed because of which one beta? At least one sp3 hydrogen, one sp3 hydrogen, one sp3 hydrogen here. One more hydrogen is there, one more hydrogen is there, which means we make it here 3 times neutral. So suppose here with respect to this bond is as it is, this bond is as it is, and you make it here this place, this one place, which one? This middle one. Next, one more you may get, one more you may get from that situation only. So double bond above hydrogen, this hydrogen, next one here H plus. So how many times we are getting what here? Positive neutral charge, neutral, which means liberation of H plus here. Now double bond is not there, positive charge with respect to this hydrogen neutral, with respect to this hydrogen neutral, with respect to this hydrogen also neutral. So which means here the stability means many times we are getting 0 0 0. So the stability of carbocation, the stability of carbocation is directly proportional to number of alpha sp3 hydrogens. Stability of carbocation is directly proportional to alpha sp3 hydrogens. So these all the structures are called what here? Hyperconjugative structures. So how to find the hyperconjugative structures? Hyperconjugative structures here, the total number of alpha hydrogen plus 1. 1 is actually parent site, where this one is a 1, first one, parent site. Next one here, one time we are getting neutral. So this one is third one, this one is what? Fourth one. So total how many hyperconjugative structures? 4 hyperconjugative structures. There are 4 hyperconjugative structures based on this one, alpha hydrogens. How many alpha hydrogens we have? 3 alpha hydrogens. So 3 alpha hydrogen, 3 structures plus the parent one, 4. This is the hyperconjugative structure formula. So stability of carbocation is directly proportional to number of alpha sp3 hydrogens. Same logic is only for what we have discussed here, carbocation. We may apply for carbon radical also, because free orbital is what here? Free orbital carbon radical is also possible. Carbon radical, if you take here CH2 bond is there. Now one lobe is unpaired electron is there. Next one is what here? CH bond is there. Of course here it gets homolytic cleavage. I have told you in the last class there are only 2 types of cleavages, heterolytic and homolytic. Here one unpaired electron is there, that's why it gets what here? Homolytic cleavage. So radical formation, one time neutral, second time neutral, third time neutral. So it becomes what here? CH2 double bond, CH2, now formation of H radical. Next here H radical, next here H radical. Here also same concept. Stability is directly proportional to what here? Stability is directly proportional to number of alpha hydrogens. So this is sp2. A radical is sp2 means radical is not always sp2. The sp2 radical, the sp2 carbocation. Next one is, which means what? We should need one free orbital, not hybrid orbital. That's why pz, whatever it is, empty orbital or one one electron, single electron. Okay, so that is what. Next one is what here? Alkene also you may observe. Alkene, C double bond C. Next here hydrogen, here hydrogen, here hydrogen. So with respect to alkene, alpha positions we have what? 3 hydrogens. Now what is the overlappation here? What is the overlappation? This is having actually pi bond overlappation like this. pi bond overlappation. Now here what CH bond is there? This is more electronegative. En is what beta compared to sp3. This is more electronegative element. So in the influence of this one, bond is polarized towards which one? This one. Here also towards carbon. Now what is the charge of this one? Beta negative, which means it is broken like this, giving negative charge. Now this pi bond electrons, electron density is polarized towards left side carbon and giving the middle carbon is empty. So the product is what here? The product is what here like this. C minus, next one is C double bond CH2, here H plus. Okay. C minus, delocalization, this is delocalized, so last carbon is getting negative charge. This is what here? Delocalization. This is what beta here? CH bond is sigma bond, it is converted to pi bond. Next delocalization, C minus, CH bond like this, sigma. So sigma pi, this is also sigma pi delocalization. That means what here? Resonance, hyperconjugation. That means what here? Hyperconjugation. So hyperconjugation, three type of free orbitals you may get here. The free orbitals are anti-bonding pi orbitals. sp2 overall, sp2 hybridization with respect to sp2, at least one sp3, then it may show here hyperconjugation. Now the important factor about this hyperconjugation, if you observe two effects, hyperconjugation as well as inductive effects, hyperconjugation as well as inductive effect, what factor we have to consider? Two effects you may observe here. Which is a dominant effect? Which is more effective? That is important. Based on that one only you may find that stability of carbocations, carbanions, acidic or basic nature, which is more effective. So what is happening here? Actually, inductive effect is nothing but polarity of sigma bond. Certain kind of thing is there. So in the influence of this one, where it is what is polarized toward that carbon, which means electron donating or electron withdrawing to whatever. Here this is overall sigma polarity. This is what here? Sigma polarity. Polarization of sigma electrons only. Of course, sigma is a stronger bond. So it is what here? Endothermic reaction. So to polarize this one after breaking that some bond, it requires certain amount of energy. That is what here? Endothermic reaction, because sigma is stronger. But here hyperconjugation, what is happening? Sigma bond is being converted to pi bond. Am I right? Check it here, all the conditions. Sigma bond is being converted to what here? Pi bond. Of course, the breakage of sigma bond, CH bond is here. Whether it is heterolytic cleavage or homolytic cleavage, whatever it is. But here, of course, this step is what here? Endothermic reaction. Second step is what here? Exothermic reaction, because bond formation is what here? Exothermic reaction. Certain amount of potential energy is being converted to what here? I mean, it's been released to surroundings. Now it is what here? Exothermic reaction. So at least one of the step is what here? Exothermic reaction. But there is only one step, that is what? Endothermic reaction. Now which is more reactive? Which is more effective? It is quite difficult, because polarity only endothermic. Here endo and exo. So that's why hyperconjugation is more effective than inductive effect. If you observe two effects in a single molecule, single anion or whatever cation, so which is dominant effect here? Hyperconjugation is more effective. Why? The reason is what here? Two reasons. One reason is exo-endothermic probability. One more reason is what here? Electronic density. If we observe like polarity, due to polarity from 100% charge, maybe positive or negative, 100 to it is decreased to 10, 5, 20, 30, whatever the charge, but there will never be zero for inductive effect. But in hyperconjugation, you may get that condition. Here this is a positive charge, neutral. Here it is a radical, neutral, single unpaired electron to neutral, empty orbital positive charge to neutral. Yes, that's why hyperconjugation is giving more stability of that molecule, anion or cation. So that's why it is more effective. We must consider what here? Hyperconjugation. If we observe two effects, hyperconjugation. Let's see one example here. Hyperconjugation. How you get clash here in between hyperconjugation and inductive? One thing is here what carbocation is there. This is the word like carbocation. Next one here also carbocation. Carbocation is there, right? Now here the problem is what according to inductive effect. Of course it is having plus side, right? It is also having plus side. This is more effective. Which is directly connected carbon is what more effective, whether it is plus side or minus side. Second is what second carbon is also there, which means here plus side effect is more. Two methyl groups are connected. Distance okay, but here only one carbon is there. Okay, here plus psi is less. Plus psi is less. So carbocation more plus psi, more stability for which one? This one, right? That is okay. I effect according to I effect, second molecule is more stable, but according to hyperconjugation, which is more stable? Which is more stable? Carbocation is there here. How many alpha hydrogens? 3 alpha hydrogens. How many alpha hydrogens? 3 alpha hydrogens. How many alpha hydrogens? 2 only. There are 2 alpha hydrogens in the second molecule. 3 times it is getting like this. 1, 2, 3, 3 times 0, 0, 0. 3 times it gets neutral charge. This carbon. We need this carbon stability only. This is the intermediate. Actually, lifetime of this one is very less. We have to choose. Of course, in between these two unstable molecules, which is more stable? Now it is getting 3 times 0. 1, 2, 3, 0 like this. It may get only 2 times 0. Then which is more stable? 3 times stability is more. That's why here. What is the factor? Hyperconjugation. According to inductive second molecule. But according to hyperconjugation here first molecule. What we have to consider? Inductive. According to inductive what? First molecule will be more stable than second molecule. Very, very important point. Inductive hyperconjugation. If you make a clash between these two, then here multi effects. Of course, one molecule if you take multi effects, maybe there are multi effects. Maybe 2, maybe 3, maybe all, depending upon structure. So all out of all factors, which is the dominant one? What is the reason that we must know? After knowing that one, what is the dominant effect? Now here hyperconjugation is dominant according to that one. So this will be the stable first molecule. Overall stability. So first one will be more stable. First one will be what? More stable. One more applications. You make it short here. This is what here. Of course, using plus I minus I. Next one is hyperconjugation. Plus I minus I hyperconjugation. Plus I minus I and hyperconjugation. See, CH3 plus CD3 plus. CH3 plus and CD3 plus. So there is no hyperconjugation. Hyperconjugation condition sp2 atom with respect to sp2 alpha sp3 hydrogen, which means alpha sp3 hydrogen that is connected with certain kind of hydrogen atoms. There should be at least 2 carbons, right? There should be at least 2 carbons, but here only single carbon is present. So hyperconjugation is absent here. Hyperconjugation is absent, absolutely absent here. Now what is a C plus D plus? C plus D plus, we have only one effect of hydrogen deuterium, that is plus psi. That is what here? Plus psi. According to plus psi, which is more electron donating group? D is the more electron donating group. That's why CD3 plus is more stable than CH3 plus. Is it clear? Is it clear, beta? CD3 is more stable than CH3 plus. But if we take extra carbon, if we take here extra carbon, I am representing like this: CH3, C plus, CD3, C plus, right? Now here alpha sp3, alpha condition is there. What we have to select here? Hyperconjugation. That is okay. Hyperconjugation, same number of deuterium 3, hydrogen 3. Then actually in the hyperconjugative structure, what is happening? First step is what here? Heterolytic cleavage of CH bond. Now you have to choose the bond strength of CH and CD. Which is having low bond dissociation energy. So D and C, this is nucleus intensity is what here? More electron density is present in what here? Z effective nuclear charge here. Mass increases. What happened? Distance decreases. If distance will be decreased, then attractive forces will be increased. So that's why bond dissociation energy, normally bond dissociation energy BDE. So which is highest? Ct is greater than Cd. Cd will be greater than Ch. Why? Because of here mass will be increased isotope. So there are stronger attractive force between carbon nucleus and tritium nucleus, carbon nucleus and deuterium nucleus. So that's the reason here it requires more amount of energy, which means here more endothermic reaction, this one more endothermic reaction. That's why it will be easier. Of course same number of alpha hydrogens, but BDE is the matter here, bond dissociation is the matter here. That's why CH3C plus is more stable than CD3C plus. So overall order is what better here? CT3 C plus, CD3, C plus, CH3, C plus. Which is more stable here? For last one is more stable. But if you take here single carbon, CT3 plus, CD3 plus, CH3 plus. Now there is no hyperconjugation, only plus I. According to plus I, T, D, H. This will be the order. See the trend? Opposite, quite opposite. First one, what is the reason? BDE, of course, hyperconjugation with BDE. Second one, only inductive effects. So this is the major application of these two, deuterium and tritium. Of course, isotopes of hydrogen. How to apply, whether it is showing hyperconjugation or inductive. So it must be important, this one. Okay. So you must be careful here, right? So this is the trend of carbocations. D resonance over. Next one, hyperconjugation. Few more applications we have to check. Few more applications. Right. Applications of hyperconjugation. Applications of hyperconjugation. How many types of applications are there? First one, sp2 atom. Sp2 atom is nothing but here stability of carbocation. First one is what? Stability of carbocation, right? Second one is what? Stability of carbon radical. Because sp2 free pz electron is present. Third one is what? In alkenes, few more applications are there. So first one is what? Stability of alkene. First one is what? Here stability of alkene. Second one, bond length of cc. Third one, heat of hydrogenation. Fourth one, dipole moments. Fourth one is what? Dipole moment. So these are the major applications of hyperconjugation. Inductive only about the stability and acidic and basic nature, right? So here what? Hyperconjugation application: stability of carbocation, stability of radical. Alkenes, first factor stability, second factor bond length, third factor heat of hydrogenation, fourth factor dipole. Means these not are applicable for carbocations and radical. It is under only alkenes. So alkenes major important trends, these are stability, bond length, heat of hydrogenation, dipole moment. So first one, two examples of carbocations, carbon radical, carbon radical. If we take here Cc plus 2 degree, Cc plus 3 degree. Now we have to choose right here hyperconjugation, inductive, both are there. So hyperconjugation is the dominant effect. How many alpha hydrogens? 3 alpha hydrogens. How many alpha hydrogens? CH3, 6 alpha hydrogens. How many alpha hydrogens? 9 alpha hydrogens. More alpha hydrogen, more its stability. More alpha hydrogen, more its stability. Hyperconjugative. So this is the hyperconjugative. Next one, if you take here CH3, next one CC3, next one is CC3, like this. Of course, here also. So here 0 hyperconjugation, 3 and 6 alpha hydrogens. So this will be the stability order. Check it. This will be the stability order. Hyperconjugation. Hyperconjugation. So here only one factor is what stability of carbocation. Second one, in the same manner. In the same manner, of course, it may be applicable for cyclic structures also. Cyclic structures also you may take for carbocation stability, alkene stability, as well as radical stability also. Radical stability also. Next one here, one more carbocation, one more carbocation. Now there are only two types of effects: hyperconjugation and indirect, right? So this is the sp2 atom. With respect to sp2, what is the condition here? With respect to sp2, alpha sp3 hydrogens. With respect to sp2, alpha sp3. Expand in your mind here. This is ch2, which means two hydrogens. Here alpha. Here also alpha, which means how many? Two alpha hydrogen. This is also alpha, three hydrogens. Total how many here? 2 to 7 alpha hydrogens. 7 alpha hydrogens. Next here, this is what here alpha sp3. How many hydrogens? Only one alpha hydrogen. This side is what here? 2 alpha hydrogens. So total 3 alpha hydrogens. There are 3 alpha hydrogens, right? Next here, this one is the first alpha carbon is having 2 hydrogens. It is also having 2 hydrogens. So there are total 4 alpha hydrogen. Now, after knowing the number of alpha hydrogen, we can find it. Stability order according to hyperconjugation. So stability order, which will be, for example, this one is the first molecule, second molecule, third molecule, then stability order. So 7 alpha hydrogen, first one is greater, then 3 alpha, 4 alpha, third one is greater, next one is what? Second one is the least stabilized carbocation. It is what? Least stabilized carbocation. See, check it. Number of alpha hydrogen. Number of alpha hydrogen. Same thing we may apply for radicals also. Same if in terms of carbocation, if we take here radical is there here, radical 3 degree, radical is there. Next one 2 degree radical, but different carbon is there. Next here also 2 degree radical with a different carbon is there. Right? Same number of alpha hydrogen. Check it better. Instead of carbocation, just it is what placed with carbon radical. sp2, then same number of alpha hydrogens. Which means if you assume here first one, second one, third molecule, then stability of radical, first one is what? 1 greater than 3 greater than 2. This is the stability order of radical, right? You may take same concept radical for this one, CH3 radical, CC radical, 2 degree radical, next one is what? 3 degree radical, right? Yes, 0 alpha hydrogen because single carbon there is no comparative thing carbon sp3 atom. Next here 3 alpha hydrogens are there, here 6 alpha hydrogens, here 9 alpha hydrogens. So more number of alpha hydrogen, more its stability. More number of alpha hydrogen, more its stability. So this is the order. This will be the order, right? Next for alkene also. But alkene here, what is the problem with alkene? So you have to choose two directions because here in carbocation you have only one single sp2 atom, carbon radical. Carbocation also you may have only single carbocation, but in alkene you will get what here? 2 CH2 is nothing but here 2 sp2 hybrid carbons, 2 sp2 hybrid carbons. So with respect to this carbon, how many alpha hydrogens are connected? With respect to this one, how many alpha hydrogens are connected? That you have to count total. Okay, because there are 2 alpha hydrogens, 2 sp2 atoms, 2 sp2 atoms. For example, say first molecule. This one is the first molecule. Second molecule is like this, propene. Third molecule is 2-butene. Third molecule is 2-butene. Now come, simple thing here. So this is the sp2. There is no alpha sp3. It is also sp2, but there is no alpha sp3. So overall 0 alpha hydrogens. 0 alpha hydrogens. So this side no sp3 hydrogens. This side we have what? Alpha sp3, which means here total how many? 3 alpha hydrogen. This molecule is having 3 alpha hydrogen. This molecule, so with respect to this one sp3, with respect to this one also sp3, CH3 total 6 alpha hydrogens. There will be total 6 alpha hydrogens. So more number of alpha hydrogen, more it will be stabilized. It will be stabilized. So this is the order of stability. Okay. And one more important factor here. One more important factor, right? In which among three carbon, double bond carbon, this side carbon, this side carbon. Next one is what here? CH2 double bond C carbon carbon. Next one is what here? This we are taking what geometrical. So carbon carbon. Next here carbon double bond carbon. Find out number of alpha. First find out number of alpha hydrogens. First one find out number of alpha hydrogens. sp2 sp2 sp3 sp3 choose it, sp2 sp2 then alpha sp3, sp2 sp2 then alpha sp3. Tell me first, how many alpha hydrogens? First molecule is having how many alpha hydrogens? 6 alpha hydrogens, am I right? CH3 CH. Second one is also having, there is no alpha but here alpha 3 3, so will be what here? 6 alpha hydrogens. Third one, this side CH3, right side is also CH3, which means there are also 6 alpha hydrogens, right? 6 alpha hydrogens. Now, all are having same number of alpha hydrogens. All are having same number of alpha hydrogens. Then which is more stable? This is very important point here. Which is more stable? So here this carbon is stabilized by alpha CH3, means it is getting what? Sigma polarity, sigma pi polarity 3 times. This carbon is also getting 3 times. Here this carbon 3 times, this carbon 3 times, but here this carbon in the second molecule, a single carbon is stabilized by 6 times. A single carbon is participating in the stability 6 times. 3 times, 3 times. So out of 3 6. Which is more stable? 6 times of single carbon is more stable. That's why it is more stable. So very important, 6 alpha, 6 alpha, 6 alpha. But this single carbon is showing 6 times stability. So this one is what here? First one, more stable. Now in between these two, same number of alpha hydrogen, same type of carbons are showing same number of stability. But the factor is what here? Sterical factor. Factor is what here? Sterical factor. Why? What is happening? Sterical factor. This is alpha CH3. CH3 is nothing but tetrahedral geometry. It is expanded like this. Of course, it is also tetrahedral geometry. It is expanded like this. So carbon carbon, it's not even single bond. It is double bond. It's double bond. So distance between two carbons, what happened? Decreased. Now your tetrahedral geometry. Two are on the same side. So what is happening here? Spherical repulsions are generated. Here also, of course, CH3, but both are in opposite direction. So that kind of spherical repulsions are not observed here because distance is increased. There would be proper spatial orientation of this tetrahedral. Now you tell me which is more stable. First one is over already, middle one. So in between 1 and 3, which is more stable? Third one is more stable than first one. Factor is what here? Factor. Spherical factor. Electronic effects are same. Same alpha hydrogen, same carbon showing same types of what? Stability 3 times. But extra factor is what here? Spherical factor. That's why we must consider all the factors. So in between cis and trans, which is more stable here? Trans is more stable than cis. It is not always. Again, it's not always, because you may get sometimes hydrogen bond also. Many factors are there, you have to consider all. So normally without any types of extra bonds, in between cis and trans is more stable than cis. Trans will be more stable than cis. So this is the order of stability of carbocation, carbanion, and alkenes also. Only stability. One factor, two factor, three. Third one over. Remaining is bond length of Cc. Next one is heat of hydrogenation of that alkene. Next one dipole moment of that alkene. Of course, last one more is that we will discuss later. This is what here heat of combustion. Heat of combustion. Heat of combustion of alkene. Heat of combustion of alkene that we will discuss after resonating stability or resonance, aromaticity, anti-aromaticity. Then I will discuss of this one. Okay, after that. Check it, beta.